Good afternoon. My name is Dale Freed. Thank you for coming to this session. It's a privilege to be here today and to share with you some of my excitement about Geiger-mode Lidar and how it works. My co-authors and I would like to thank the conference organizers for inviting us here to present some of this recent work. Today, what we'll cover is a little bit of background about Geiger-mode Lidar. I hope one of the themes that comes through clearly is about the flexibility that these single photon sensitive lidars enable. Next, I'll be introducing our flagship new product. It's a Geiger-mode Lidar system called Cuchillo. I'll talk a little bit about how it works, what's unique about it, and show you some imagery, and we'll talk about some applications. And just as a teaser, on the right there is an image from this system, and I'll tell you more about that. So, what's the big deal about Geiger-mode Lidar? Well, or single photon sensitive Lidar is a more general term. These are Lidars that on the receive side, they detect and timestamp individual photons. There's several technologies that can be used to accomplish this photon by photon detection process. I'll talk about what I know about, which is Geiger mode avalanche photodiode arrays. There's also Mercad telluride APDs, which we'll hear about in another talk. Microchannel plates, you can get spatial resolution by having segmented anodes. There's nanowire detectors, photomultiplier tubes. But when you put these things together into a large array, one of the promises here is very large measurement rates. Now, let me talk just a bit here about a sensor chip assembly of one of these Geiger-mode APD arrays. It's an array of avalanche photodiodes. This is a cross-section here showing kind of a cartoon of how this works. The incident light is back illuminated. It comes through the substrate, goes into the absorber region, and some is absorbed there. Now, the idea here is that you bias these diodes, these avalanche photodiodes, slightly above what's normally considered the breakdown voltage. And here I'm showing this voltage that we just kind of touch it a little bit, tickle it, and bring the charge up the capacitance slightly, a few volts above this breakdown voltage. It's then what's called an arm state. And when something like a single photon hits it, you have a avalanche process that it's kind of a runaway amplifying avalanche because, again, you're above the breakdown voltage. The point is that you can get a multi-volt drop on this node of your circuit here as a result of a single photon, and this can happen with low jitter. That big signal means that you can make a digital timing circuit behind each pixel. These are small and simple enough that you can fit them behind every pixel. And what comes out is a digitally encoded photon arrival time for each one of these photons that you detect. So you can make big arrays, you have low timing jitter, and you have good sensitivity to single photons. And these are commercially available. So we can get measurement rates on the order of 100 million to a billion detected photons per second. All right, the next thing, how do you normally operate one of these systems? Typically, we operate it so that the data is collected at a density of approximately 5 to 30 detected photons per measurement that we're trying to do. And here I'm defining a measurement as the process of localizing one surface in three-dimensional space in some sort of a final product that we're generating. So in order to provide a reliable measurement in that final product, that signal from that surface must be stronger than the noise sources, strong enough to reach whatever the desired confidence intervals are. I'll talk about that more in a few slides. Now, again, the reason that people really get excited about this is down here near the bottom, you can get these very high measurement rates, talking about 10 million to 100 million of these final kind of high confidence measurements per second. And just to put that in context, if I was trying to do 100 points per square meter, for example, that means I could collect a square kilometer every second. People get excited about that, and with good reason. Another thing that's important is that because we're doing this digital post-processing, we can aggregate signal collected over many laser pulses. We can have a long integration time and therefore sort of an arbitrary range. I'm not going to go much more into that in this talk. So again, how do we exploit this flexibility of being able to do this digital post-processing? Well, let me talk you through how we typically use these systems. A LiDAR will scan the ground as maybe an aircraft flies along. This is in an airborne mapping application, for example. Each point on the ground is interrogated. That means we shine light on it from the laser, maybe between 100 or 10,000 times. There's a big variation because there's a lot of variation in what you're trying to do and accomplish. The imagers that we project onto the ground, or that we image the ground with, range from 32 by 32 pixels up to some of the biggest ones today are 128 by 256s. So high numbers of pixel, high measurement rates. And we plan our data collections so that we collect the desired amount of signal per resolution element or per measurement point on the ground. We've collected the data, now what? So in the processing, the first thing we do is we take all of those detector firing events, be they from signal or ambient light or dark counts inherent in the detectors themselves, or even crosstalk effects, which I won't get into, but you project all those into 3D space. And then we comb through that 3D point cloud and we're looking for concentrations of points. We're going to interpret those concentrations as arising from real surfaces. Diffuse background noise is not correlated in time with that laser pulse that we keep hitting the ground with. And so we're going to interpret kind of diffuse background stuff as not being signal. And we can remove that with various thresholding schemes that people have worked long and hard to perfect. Now, I'd like to say a little bit about these confidence intervals. And you may be familiar with a ROC curve, a receiver operating characteristic. It's basically a plot of the probability of detecting the thing you're trying to detect. In this case, it's a surface. And the probability of falsely claiming something as present when it really isn't. And we can use the basic statistical distribution functions of a Poisson distribution for the arrival of photons and a negative binomial distribution for the firing events of these detectors. Using those distribution functions, we can draw these curves on here. Now, each curve is for a different amount of signal light that we got from the ground. And I've shown somewhere between 5 and 25 photons that we detect from the ground. And each point along one of these given curves is related to the different amount of thresholding that we might do. You could, for example, on this curve, you could set your threshold very low. Basically, I got 1 photon here, and you would have a very high probability of detecting that surface. So that's good if you're looking for vertical obstructions when you're trying to land your helicopter and you really don't want to run into anything. But you have a high rate of false alarms. On the other hand, if you're doing something like trying to make a really good floodplain map and you don't want any noise in it and you just want to know where the smooth ground is, then you would care more about a very low false alarm rate. And so you could set your thresholds much higher. So again, the different curves tell us about the amount of laser energy that was used in the detection or in the scanning process, and the point along the line tells us about thresholding. So that's how you typically do this. Now, in fact, in reality, you're going to start with a desired in the data product. And I alluded to some of those before, helicopter landing zone versus floodplain. For example, there's many different ways that you might choose what confidence interval you'd need. So, you pick a probability of detection and a false alarm rate, and you say, okay, that tells me the amount of signal photons that I must have, the amount of laser energy that I'm going to have to put down, the size of my apertures and all that. And then from that, I work out the collection parameters that I have to use. And in order to really realize that full promise of these Geiger mode systems, the flexibility that I talked about, you need to have a LiDAR system that allows you to vary the swath width easily, the platform speed, the pulse rate, your laser power, the amount of angular diversity that you're using, all those kinds of things, so that you can tailor the collection to get just the right amount of light. Well, This is where I'd like to say we have a system that is now available for lease or for purchase. We've done downrange field demos for US Southcom. This system is optimized for commercial and security applications. The optimal altitudes are between 3 and 12,000 feet. The best value for the customer is realized when they're trying to do something that requires a pretty high point density, maybe 30 to 300 points per square meter. That's useful if you're doing something like poking through forest canopy, or if you're trying to produce a really precise digital twin in a complex urban environment. The system has high angular diversity, meaning we can interrogate points on the ground from many different angles easily, and it's also optimized for affordability. I'll show you a video here of a 1 kilometer diameter circle that we collected. This was from 10,000 feet. This was a single pass, about 30 seconds of recording time here. And this video is a screen capture of a point cloud. It shows a lot of the detail here around the buildings. You can see lane markers in the roads. These are power lines here. There's a cell tower over here. You can see the building roofs and the foliage. Now what I'd like to show you is what happens when we do our digital defoliation. We turn off the treetops and we look just down at the ground. Some folks have had trouble seeing the ground with Geiger-mode LiDAR. It actually works very well if you do the collection optimally. Here you can see trails. You can see a little stream down under here. And again, just to remind you, there is actually some significant canopy here. Let me talk you through some of the key characteristics and differentiators of the Cuchillo LiDAR system. First of all, the measurement rate. We're very proud of these high measurement rates in the Geiger-mode LiDAR community. This particular system, with the lasers that we have and the aperture and so on, a good number to work with is about 10 million points per second from about 8,000 feet, looking at typical scenes with vegetation and some urban areas. Those high measurement rates, as I alluded before, allow us to do multi-look collections at high post spacings. We can do detailed city mapping. We can do through canopy imaging. In the next chart, I'll go through our scanning system in more detail, but a key takeaway is it's a dual axis scan system that allows us to point anywhere within a 40 by 40 degree field of regard. It gives us tremendous flexibility. And then we have scan modes that allow us to scan particular regions of interest that we define by their coordinates on the ground. The scan pattern is quite uniform, and having a detector array, a camera that's imaged onto the ground, gives us very good sampling uniformity. And what the consequence is in products that you give to your customer, you have reduced artifacts, and it also makes the processing a bit simpler. Our range resolution is sub-nanosecond, which means we can differentiate closely spaced surfaces in the range direction, and it also reduces range walk. The system, as you can see in this picture, is pretty small. Currently it's about 200 pounds. This is our prototype system that we flew operational in South America. The power requirements are very manageable as well. It's easy to put into an aircraft. We've had it in a King Air. Other platforms are very possible as well. Let me talk a bit more about the scanning, because this is an important component of giving us the flexibility to exploit what's possible with Geiger-mode LiDARs. The key point is you have a certain rate that you can do measurements. You need to put that light in those areas on the ground where you're most interested. Give the customer what they paid for and don't waste their money on collecting things that are of no interest. So there's 3 ways that we can operate our system: target mode, corridor mode, and mapping mode. So target mode is when you have one of those smaller areas of interest, maybe a few hundred meters to a few kilometers in size. Corridor mode is more for these long meandering ribbons, be they power line corridors or rivers or borders, highways. And then map mode is these much larger regions where we have to take many swaths. Mission planning is straightforward, and the way we fly these things is like this. So for a target mode, we might come in, take one pass, and look to the left, and we continuously scan maybe 10, maybe 30 times that area on the ground as we fly by. Then we turn, we do the next pass, and we turn, we do the next pass, and so we're getting that that scanned area from all sides. We mitigate shadowing that way. We can poke through foliage canopy that way. In corridor mode, we tend to fly a straight line, and as we fly along, we precisely define the corridor coordinates, latitude and longitude on the ground, and as we fly along, the system automatically follows that corridor. So again, it puts the light where we need it. We can also get multiple different look angles on one pass along these corridors, looking forward, down and back as we fly along. Let me show you a video of some data we've collected here. This is just as we were having fun with this collection, we wanted to show what's possible. And so the data that I'll show is 2 passes that were taken. This is about an 8-kilometer long strip that we defined, again, using coordinates on the ground. At the airport end, it's about 1 kilometer wide, and then it narrows down, as you can see. Again, this was collected about 10,000 feet. This movie is projected onto Google Earth just to give some context here, and you can see the flight paths on each side. As we zoom in here, you'll start to see, the runway markings and such. That's a pretty normal thing. You can see all the canopy here. There's a highway that comes in, and you can see the lane markings. On the road, you see a power line corridor going along here. The local Lowe's store is there. And then there's a high power line that comes in from the side. We've necked down the collection because here we said, let's demonstrate what we can do in just a narrow corridor. So again, we're focusing all of our collection capability on just the areas that we're most interested in. As we follow this power line corridor further, we come into a substation, and you can see the lines coming in and out of that. I'll just note that this is all of the data we collected. This is not trimmed down from a much larger collection. This is what we collected, and it really shows you the ability to focus the light where we need it. So that's corridor mode. There's also the wide area map mode. In this example, we did 4 passes for this example collection over Richmond. Here we're at 8,500 feet. We did 2/3 swath overlap, and what we were trying to demonstrate here is the ability in a wide area mapping sense to get a lot of angular diversity. So with 2/3 overlap, what that means is each point on the ground gets imaged on 3 different swaths. So that's good. You can have, straight down, left and right, or north and south, or whatever. In addition, on each of these swaths along, we arranged things so that we scanned each point on the ground from 3 different vantage points. And so 3 vantage points per swath, 3 swaths, that gives us 9 different look angles that we were able to collect from in a very straightforward manner, just in our flight planning. And finally, I'll show you some higher resolution imagery. Here, we're focused down from 6,500 feet, so a little bit lower, on a 250-meter diameter circle at our favorite airport here. And the idea here was to show the level of precision and point density that we can get. This is 1 second of data. It's one part of about 20 scans that we collected as we flew over this area. At that kind of revisit rate, it's kind of fun to think about how you could see movers moving throughout this scene. You basically make a movie with one update per second. The imagery here in this picture is processed to 25 points per square meter, 20 centimeter post spacings. But we can also process the exact same data differently. So let's zoom in on this parking lot, and what you see here, we processed it to 10 centimeters. So it's the exact same data, it's just our binning is a little different. So that means on that rock curve, we're now at a different point. And what we see is more speckly patterns. There's more voids, places where we just didn't have enough photons within that smaller box size to declare the presence of a surface. But where we do have enough signal, like these lines and that sort of thing, you get better resolution, better spatial resolution. The voids on some of these cars, like over here, are kind of indicative of finishes that maybe are highly reflective or highly absorptive. This is an example from the Mooney Dam. It's a reservoir in Virginia. This is data from 8 passes. The actual amount of data that's used to make this image is actually only less than 1 minute of recording time. And you see a significant amount of foliage, a power line coming in here. But what I'd like to show you is the ability of this system to penetrate through heavy forest canopy. So this is the same day we're looking at it from the side. The spillway of the dam is over here, and we take a transect. And a transect is just a thin vertical slice. We go through the point cloud and we just take out and collapse into this 2D image here all the points that are within that thin slice. And you see very clearly there's a really solid representation of the ground layer. We really nailed that. You can see the tree heights are, somewhere between 30 and 40 meters. So these are big, tall trees. Just for context, the power line that goes through here is way down here. That's only about 10 meters above the ground, as one might expect. But you see, whatever branches intersected that transect, that thin slice, that's what's showing up here. So I'll just assure you that Geiger-mode LiDAR is used on a daily basis very effectively for poking through very dense tree canopy and seeing what's going on the ground. I'll quickly walk you through some of the technical specifications of this sensor. We have 2 versions, the A version and the B version. A is a 16-watt laser. The B is a 40-watt laser system. The eye safety distances are very manageable, and this is for the worst case of someone on the ground with 7x50 binoculars staring at the sensor while it simultaneously is staring at the person for 10 seconds. So very conservative numbers here. The main difference between the A and B version is the B has 2 cameras integrated into it, and so the measurement rates are higher. The link, both the recording rate is twice as high for the 2 cameras, and the link, meaning the number of detected photons per second, is higher by about the ratio of the laser powers. Range resolution is good. Angular resolution on this system is about 100 microradians. That's useful when you're flying at these lower altitudes that it was optimized for. And we'd certainly be, we're very familiar with systems that have much higher angular resolution and would be happy to work with people on those. Let me talk a little bit about the collection capability of this system. What we're plotting here is the instantaneous area collection rate. So if we're out mapping, we're just running down a swath, how fast can we scoop up imagery? And in square kilometers per hour, and I've put it on a log scale because we like straight lines. And we're plotting that as a function of the aircraft altitude. And let me walk you through how we think about these things. On the left side, the limit is set by the scan width. Our scanner is only able, as I said before, to interrogate a 40-degree cross-track field of regard. And so projecting that onto the ground from these lower altitudes absolutely sets a limit on our area collection rate. Here we've been pretty sporting with our aircraft speed, but it's certainly something that a lot of aircraft can do. Over here, the limit is set by the link. Remember I said we need something like between 5 and 30 detected photons per measurement in order to meet our imaging goals, depending on what those are. So as we go up higher, 1 over r squared makes this fall off. It's not perfectly straight because I put in a little bit of atmospheric absorption in this calculation. But it's basically these 2 limits that limit our area collection rate. And this is all done assuming that at the end of the day, we wanted something like 200 points per square meter in our final data product. Now, sometimes you don't want that. Sorry, let me introduce also the resolution. This is the 100 microradians projected down onto the ground. So that's our full width half max spatial resolution. Sometimes 200 points per square meter is not what you're looking for. So if one line is good, more or better. So red is 500 points per square meter, all the way up to blue up here, which is a few points per square meter. And as I alluded, depending on what you're trying to do with this system, you would like to operate it in different regimes. So for example, if you want to poke through canopy but you're trying to interrogate the ground to see what flooding might occur. So you're trying to get a good ground model, but it doesn't have to be. You want a good vertical accuracy, but you don't need a lot of spatial resolution. Maybe you're working up over here, fewer points. On the other hand, if you're trying to do foliage penetration to look for people under canopy, yeah, you want a lot of points. You want to do a really good job of high resolution and a lot of points. And so you operate more like down here. Again, flexibility of these Geiger mode systems allows you to, with one piece of hardware, do lots of different tasks. So to conclude, remember we talked about Geiger mode LiDAR flexibility allows us to optimize, and I talked to you about this rock curve. We want to collect just enough light to achieve our measurement goals. We also talked about Cuchillo, this LiDAR system that's our product that's just coming out. And we talked about the different ways of doing those collections. We're putting the light just where we want it. And then I showed you some example collections, both a transect through forest as well as high density imagery at an airport with high levels of detail. So with that, I'll stop. I'll thank you for your attention and be happy to take questions.